Okay. I think the mic is okay. Good morning, everyone. Hello. Welcome to Voxed Days in Grid. For the first time, welcome to all of you. It's really great to be here today with you. So, are your tests good enough? I'm here today to make you rethink and reapproach your testing strategy, your review process, your QA methodologies, TDD approach, and your refactoring routine. But who am I with all this? Who am I to challenge all of this and with all of this question? I'm Michalis Zampetakis. I'm a senior software engineer currently working at Zedita. I come from the sunny island of Crete. But apart from this stuff, I also enjoy being with people, discussing things, exchanging ideas, and sharing experience. So I also help organizing other cool stuff in our island, such as Socrates Crete, a yearly open space and conference about the software crafting and also dev stuff, the developers community here in Crete, which runs for more than 10 years with regular meetups. You can find more details in my social media under the Zampetakis tag. So, in this talk, this is the agenda for this talk. I will start talking about code validation and code coverage, what are they, how we can use them. Then I will move on to code mutation and mutation testing, how it is, how to use it, some challenges that mutation code has and that mutation testing has, and how and when to use and not to use, in my opinion, mutation testing. And we'll sum up with some takeaways from this presentation. This talk contains, of course, personal views and opinions. It's not affiliated by any product or company. And throughout the presentation, I will stop to do some hands-on demos. Hopefully everything will go fine, but let's see. So, how do we validate our code, the code that we write? And what do we mean by validate? By validate, we mean that the code does what it's supposed to do so, but also it doesn't do what it's not supposed to do so. So if, for example, you have a payment method that you want to validate, and you expect from that thing just to process the payment and nothing more, obviously, you don't want that same method to send an email to your customer or to another person. Obviously, the answer comes easily. Tests. Tests are always our insurance policy in the code we write. But this generates a lot of more questions in my mind, hopefully to yours. How would we assess the quality of the tests we write? There are many things we can do for this, and I hope that most of us do, at least some of them. First of all, we can review our tests as we review our code. I know it's not an easy process, it's intensive, it's not consistent as the code review, and it also has a slow feedback because we have to open a patch, request for someone to review it, wait for it, get the feedback, and do some action, and maybe redo and redo it over again. We can state that, okay, AI wrote the code, but it wrote the test as well, as Sander showed us this morning. But yeah, I won't comment on that. You had to take the red pill. We are all rockstar developers. Yeah, you are, but mistakes are here for us, for our code, and for our tests. We do TDD. In the TDD, it's a process where you write the test, a failing test, and then you write the minimum code for make the test to pass. Refactor the code and the process over and over again. But even with that, there is no way to ensure that you can safely refactor your tests or that you didn't write any excess code to make the test pass. So it comes to my mind such more of an older problem. If we have the tests to assess the quality of our code, how would we assess the quality of the test we write? It's like who will guard the guards, you know, the problem? Of course, code coverage is a tool that is commonly used. It's a measure that is commonly used to assess the quality. No. Code coverage is a quantitative metric that states that measures to which degree a program is tested by a particular test suite when it's run. Of course, there are different types of code coverage. They measure the lines that were executed during a test suite run, branches, functions, paths, loops, how many iterations, conditions, and even more. The most common one is line that we usually use. So let's see some things in action. I'm going to use Golang. I find it really easy to comprehend, and I primarily use it. So I have here, I think you see it. Is the font right? Is there anyone that cannot see that on the back? Should I increase it a bit? Better? All right. So I have a simple function. It's a function that implements the fizzbuzz. For those who don't know, it's a simple function used for demonstrating things. It gets an integer, as you can see here in line 11, and returns a string. And if the number is not positive, it has to return an empty string. If the number provided is divisible by 3 and 5, it has to return fizzbuzz. If it's divisible by 3, it has to return fizz. If it's divisible by 5, the buzz. Otherwise, it should return just the number as a string. And of course, I have here some tests to test that function. In Go, it's pretty common to use table test, where you describe different inputs and expect the appropriate output. And then you run the code and you make the assertion. So if we go to run this thing and tell our ID to calculate the code coverage, we get a pretty good code coverage. It's reported down here, 77.8%. And if we go back to our source code, we can see there is a mark next to each line that indicates if the specific line was executed during our test suite run. The green ones and the yellow ones means that it's executed. The red ones, it's not executed at all. And this thing, the yellow ones, says us that it's executed, but it's not covered all of the possible variations in the condition. So if we want to achieve an even better code coverage, I have here this exact same code, but I've added a few more cases, as you can tell here. So if I'm going to run this thing, we are happy we got 100% code coverage, and we can proceed. But I have one more example here. It's the fizzbuzz again, some tests, a little bit different numbers this time, but as you can see, I will run this thing, I will get 100% code coverage, but in the end, someone can tell me that, okay, you invoked the function, but you did not do any assertion at all, you see? So I could even get the value and assert that I just got a string, a non-empty string, or anything like that. So, back to our slides. We saw that executing code and testing code is not the same thing. So it's, as Dijkstra said, program testing can be used to show the presence of bugs, but it cannot be used to show the absence of them. So, code coverage tells us what has not been tested for sure. We are not sure that the code that we saw earlier as green, with green marks, is actually tested. But we are sure that for the rest of the code, it's definitely not tested. So, if we want to achieve a high code coverage, someone might start doing weird things in their tests. We can partially test, or we can do not assert the values, or maybe we cannot assert the type of error, which is a pretty common pitfall in our code coverage and our tests. So, this can cause this problem. When we try, as the Goodhart's law states, when we try to measure things and add a target, this tends to be not a good measure for our system. So, there's a simple thought to overcome this issue. So, if you want to know whether your test suite actually works, go back to your code and introduce a bug. Then, check if your tests can find that bug. It's something I tend to do personally when I write the code and the tests, or vice versa, and everything works smoothly. From the first time, I'm a bit worried, and I'm thinking, did I actually test that thing? Did I assert the correct values, and everything was as expected? And then I go back to the source code, change some things, rerun the test, and I think that it's failing, and I feel better. So, let's see this in action. Again, the fizz buzz, some tests here. Let's run the coverage to see that everything is fine. We got a full coverage here. And if we go back to our source code and someone states, OK, I know better, this shouldn't be less than or equal. We should do it like that, because I know better. And we go back to our tests and run this thing. You see, it failed. So I feel safer now. Everything is fine. And I know that my tests actually work. So, let's see some terminology for these things. We made a small modification to our code. This is called a mutation. And the code we generated is called a mutant, or a mutated code. So, if a mutant, as the one that we generated previously, does not cause any test to fail, we say that it survives. But if the mutant causes at least one test of our test suite to fail, we state that the mutant was killed, as we saw in our example previously. So in our example, killing is good. We want to generate mutants, and our test suite being able to kill as many mutants as possible. Of course, there are a lot of different mutation operations that we can apply in our code base. We can change the comparator types, as we did in our example. We can change the operations between values. We can change the values themselves, even if they are numbers, strings, or whatever. We can invoke different functions or completely remove some code. We can change partially a condition in our code, or remove it completely, swap it with another value. We can inject exceptions or errors, whatever we can think. So, if we automate and repeat this process through a consistent way, it seems reasonable that we will get really meaningful results for our tests and their effectiveness over our source code. And as expected, there are tools out there and libraries that can do this for us. And this is the process that we did earlier. We generated the mutant, we ran the tests of our code, and if no test failed, the mutant is considered as kill, and we are happy. If no test failed, the mutant we say it survived. So we have to go back and take some action, either by fixing the tests or adding some more cases or changing the inputs of the tests. Of course, it makes sense that we need the good code coverage for this thing to work, because if we don't have enough code coverage from our tests, all the mutations that we apply in the code base won't be killed by the library, by the tool. So these tools, what they do is that they mutate the code with different mutation operations, as we said earlier, and they run it over and over again, this process, for every mutation, and we get the result. What is the result? of course, the analysis, but they also provide a mutation score. The mutation score is the ratio between the mutants that were killed to the mutants that were generated. So if, for example, the library generates 50 mutants for our code, and 40 of them were killed, we can say that we have a mutation score of 80%. So let's see this in action again. Oh, nice. So the FizzBuzz is here again. Then our test cases. I'm going to run the test coverage. We have a good code coverage again. And then I'm going to use 06. I'm going to use the GOMU testing library. It's a bit old one, if you ask me, but it's really verbose and I really like it. So this will start generating different mutations of our source code of the FizzBuzz function as using the mutation conditions, the mutation operations, run the tests for every mutant and decide and check if at least one test failed or if all the tests passed. We see here when we have a report that it passed, it means that at least one test failed for this mutation. So the mutant was killed, and we are happy. But there is a case here that states that in this mutation, where the mutation changed a number from 0 to 1, no test failed. So the mutant survived, and we have to go back and take some action. The case is actually here. The mutation went here and changed this to that. I think it's obvious. So what we can do now, we have to take some action and improve the tests. So if, for example, I go here and add one more test for a value close to the boundary, the 0 boundary, pop, pop, and we expect the 1, hopefully we will grab this mutant. Before moving on, the mutation score is here. It's 96.5%, and it says that it generated 29 mutants, and one of them survived, and that's the failed one. So if we run this again, right, it will start again the exact same process. It will generate all the mutants and run all the tests for each one of these mutants. And now we will probably see that all of them are killed.
Can I ask you something?
Yeah, sure.
How does it decide which mutants to use? How does it generate these mutants?
It generates all of them.
Based on what?
Based on the source code. It goes here and changes everything that's possible. Change the comparison here, the numbers, as we said. It will go to change this to that maybe, or this to that, or whatever. So it's really a brute force operation, all this thing, and it takes enough time, as we will see later. Yeah, going back, we see that all mutants were killed, and we have a 100% mutation score. And now, if we go back to our previous example, in this example where we achieved 100% code coverage without actually testing anything, and we tried to run here the mutation testing, we will definitely some interesting results. You see? Every mutation survives. Our tests does not assert anything, so they don't work at all. and that's we get a 0% of code mutation. So back to your question, you see here the different, we can see here the different mutations that were applied. Yeah, change the number here from 5 to 6, change the number, the equal to 0 equal to 1, again the number here, and the number again, and so on and so on. So, we saw earlier that code coverage tells us what definitely has not been tested. Now, mutation testing tells us which code is actually tested by our tests. So, that's a proper way to test and assess the quality of our existing tests. You will ask me, does this actually work in real life? What I mean here, we went to our code and we introduced some simple bugs, some artificial bugs, and then we ran our tests to see if they can grab them, they can identify these errors. Are these the real bugs that we expect from our code, from what we write in every day? Actually, up to a point, yes. There's the coupling effect analysis that states that by explicitly testing simple faults in our code base, we are implicitly testing for the more complicated ones. So, if your tests are sensitive enough to detect small faults, such as the one that we saw earlier, they will be probably sensitive enough to grab the more complicated ones. And apart from that, imagine what these minor bugs how these minor bugs can affect your product, your project, and how significant impacts they can have in your customers, in our customers, or whoever who uses our code. History has proven that, and not so far away. Of course, mutation testing comes with its own challenges. The first challenge, and the first issue of code mutation testing are the equivalent mutants. They consider to be a problem, but let's see what are these through a demo, through an example. New test. So I have a slightly different example now. It's a really simple function, a really dummy one, that gets, given two numbers, it returns the minimum of them. You see, it's really simple and a bit dummy if you ask me. But let's see this, what will happen. I have the code here, the tests. Let's run the coverage to see how it goes. We're happy, we get a good code coverage here. Everything is green, we tested every scenario. But let's mutate this thing to see what will happen. Oh. Yeah, not a good mutation score. Let's see what happened. It states here that it changed this comparison to this, and this to that. And if we go back to our code and check it, it's pretty reasonable, right? So if I change this to that, it's not the same thing, but the result will be actually the same as the one we expect. Or if we add it like that, or vice versa, and that. Given that mutations, it seems reasonable that we cannot write any tests for this code to kill that mutant at all. So because the result will be exactly the same as the one we expect, we cannot kill that mutant. So this indicates something for our code. Of course, it's not a very well-written code. So I have here an even better version of this thing. And of course, some tests again. Let's run the coverage. It's again good enough. It's 100%. We covered all the cases. And let's go and run here again the mutation testing. So, even in this example, we can see that there is an error here, a mutant that wasn't able to be killed by our tests, that changed this to that. Again, we see that we are not able to write a test for this thing to get it killed. Okay? So, these are some equivalent mutants. Equivalent mutants are mutations that it's not possible to write any test in order to kill them. So it's more of a prompt to do something. And if we see some mutation that cannot be killed, we have to do a few things. First of all, as we said earlier, we have to go back and fix the tests, or add more test cases, or change the input values of the tests. It also can be an indication that we have some redundant code in our source code, and we have to go back and check it. And it might be an indication that we have to refactor somehow our code in order to grab that mutant, to write something better. So, equivalent mutants are considered to be a problem, even though it's really good in finding redundant code and code smells and things like that. It's a problem because it requires human intervention. It requires someone to go there and check that mutant and why it failed. By failing, I mean it wasn't killed, and take some action. The second issue of mutation testing is obviously performance, as we said earlier. I have a small example here of a library, the Logrus library. It's a common logging library in Golang, which has a good code coverage, 80%. This library requires 2.7 seconds for their tests to run. So if, for example, we generate 200 mutants, and this is a really low number, believe me, this will require, if we do the maths, 9 whole minutes for the mutation test to run. And consider that this time does not integrate the time that the library took to change the code and also to recompile before running the tests. Also considering that some mutations can generate panics or exceptions that we do not handle, or even timeouts, this time can even be bigger. Of course, there are some optimizations that mutation testing libraries do for us. They exploit modern multi-core and multi-thread processors that we now have in order to compile tests multiple times at the same time. There is a kill-fast operation that when a mutation is generated and the tests start to run, if one test fails, there is no need to run all the test suite to the bottom. The mutant is killed, so we are fine. We can skip all the rest of the tests for this mutation. Also, these libraries profile our tests in order to run the fast tests first, so that if they can kill the mutant, we can save some time from running the slower tests. Also, tools apply mutations only to the code that is already covered by our tests. If some part of the code, some lines of the code, is not covered by the test, there is no reason to make some mutation to these lines and run the tests. We are sure that the tests will fail because they're not covered. And last but not least, most of the libraries, I think nowadays, do not run the full compilation cycles from scratch, from the source code. What they do is that they exploit these trees. These are the abstract syntax trees, as we say it. It's a data structure that represents the program structure. This is an example for this little code. And it is an intermediate representation that is used by compilers between the source code and the actual binary. So these libraries, these tools go directly in there, in the abstract syntax trees, and apply the mutations on that thing instead of the source code directly. So this is really good to know if someone is going to contribute in such a library or write its own, because you will working with these things. So, are these enough for our huge code bases to achieve good performance and be able to run mutation testing, which might take hours, days, weeks, I don't know, maybe? Of course, there are more techniques that we can and we should apply in these tools. We can exclude specific code to be mutated for any reason that someone wants to do so. We can exclude specific mutants to be applied in our code. For example, I don't want this library to remove completely lines from our source code because it's not something I expect to be done. We can avoid extreme mutations. I don't want to return errors in the middle of nowhere, just for no reason. And we can always run mutation testing periodically. It's even better rather than running it never, even if that takes too much time. But if you ask me, it actually doesn't matter. I don't think someone has to write 10 tons of code, or 10 kilos, I don't know how to measure the code nowadays, and then put it overnight in my CI, in my supercomputer or super laptop, and run all the mutation testing for this code and their tests. I will get a lot of results that probably I will raise my hands and say, okay, I don't have time to deal with that. So, what can we do? In an example of the TDD approach that we said earlier, where we write the test, the failing test, write the code to make the test pass, refactor the code, and process it again, we can introduce the mutation testing part in the refactoring process, where you write the code to make the tests pass, and then you run the mutation testing to check and assess the quality of our tests, but also at the same time check if we wrote any redundant code that wasn't expected to do by our tests in the TDD. Also, there are other methodologies apart from the TDD that we can use the mutation testing with. First of all, it's not necessary to run it over all of our source code. We can analyze small pieces of code. For example, the code I'm just writing and I'm testing, and I want to reassure that the tests that I just wrote are good enough to test and to actually test the code that I wrote. We can even integrate with the version control systems, and when someone opens a patch, run the mutation testing over the code that was introduced and run the test for that code and mutate this code only. We can even decide to run mutation testing on critical parts of our product, of our code base, in the payment systems, let's say, in the whatever is critical for our domain, for our business domain. Of course, you can apply it in integration testing. If you think this is a really critical part for your business, you can apply mutation testing in integration test, which is even more expensive, but it's another way of assessing the quality of the tests and the code at the same time. You can also use it to refactor a complex code, a code that was given to you, or you just wrote a few years ago and you have no idea what it does. And there are a few tests there, but you are not sure that these tests are enough to assess the quality of your code and get all the different paths and the variations of the code. Also, we don't have to care about the score. Even if that score is the mutation testing score, the code coverage score, it's a number. We have to care about the feedback that these tools and these metrics give to us and take some action from given that feedback we get. It's a tool, not a number. You have to behave wisely, to use responsibly the tools, and depending on your way of programming. So, some key takeaways from these things. We saw that code coverage is not test coverage at all. We have to write tests for a reason, choose our test inputs wisely, and apply them in our tests. We have to aim for high code coverage, but not being an explicit target for our team or for ourselves. It's good to have it, but if you make a target, you will lose the target. If you try the mutation testing, you have to choose the mutation library and consider the things we said earlier about the performance, the different options that it provides us, and all of these things. Because if it's not something that you can incorporate in your routine, it's something that you sooner or later abandon. So, regarding mutation testing, we saw that it completes our test suite. It can find missing tests or missing cases or incomplete tests. It's more or less a safety net for refactoring our code and also our tests. It can find redundant code and code smell, as we saw earlier, through the equivalence. And it's a way to reapproach the development process we currently follow. Okay, I have here some reference used for this presentation, and yeah, that's all from me. Yeah. I don't know if you know these guys. My favorite mutants. So I think we have some time for discussion or questions, so we can meet outside and discuss.